The checklist is done. The suit is sealed. The airlock is cycling. Outside, the storm has been running for 2 days and shows nothing in the pressure readings that should stop an EVA. The wind is not strong enough to knock a person down. The visibility is low but workable, and the solar array that needs attention is 12 minutes away. The threat model says dust, abrasion on visor seals, reduced panel output, grit in mechanical joints, all of it manageable with the right procedure. The storm doesn't need to get inside the suit. It only needs to touch the outside once. The glove reaches the airlock hatch. The charge differential between the suit and the grounded metal has been building since the storm began. It makes no sound, it gives no warning. The discharge takes less than a millisecond. That is the kill mode that does not appear on most EVA checklists. The standard picture of a Martian dust storm was assembled for decades of orbital imagery, lander data, and one very influential film where the danger was wind speed and flying debris. That picture is accurate as far as it goes. The storms are real, the abrasion is real, the solar panel degradation is real, the visibility problem is real. What that picture leaves out is what the dust is doing electrically. Not to the panels, not to the seals, but to every semiconductor component inside every piece of hardware the crew relies on to stay alive. Because on Mars, dust does not just move, it charges. On Earth, static electricity is a minor inconvenience because the atmosphere continuously removes it. Every surface exposed to humid air is slightly conductive. Charge that builds up on one object bleeds away through that thin film of moisture before it reaches levels that matter. This is so automatic, so invisible, that most people never think about it as a physical process. It is simply the reason that shuffling across a carpet in dry winter air produces a spark when you touch a doorknob. Because the humidity briefly dropped, the moisture film thinned, and the charge that would normally drain away in milliseconds had nowhere to go. Scale that single spark up to a planetary surface with relative humidity near zero. Replace the carpet with billions of dust particles grinding against each other in continuous collision, and replace the doorknob with the only pressurized suit between the astronaut and vacuum. Mars has no moisture film. It has no natural ground path. What it has is fine-grained silicate dust moving in suspension at storm densities of billions of particles per cubic meter, each collision transferring electrons between surfaces in a process called triboelectric charging. The particles do not need to be large. At roughly 100 microns, about the width of a human hair, each individual grain has enough surface area to carry a measurable charge, and in a storm volume, they are colliding millions of times per second against each other and against every surface they encounter. The charge does not leak away. There is nowhere for it to go. It accumulates. The voltage that accumulates is not the voltage of a carpet shock. Electromagnetic modeling and Earth analog measurements in hyper-arid environments suggest Martian storm charge potentials reach thousands of volts across the storm volume and against isolated conductive objects. That number matters more when you know what it means for arc formation. On Earth's surface, the atmosphere is dense enough that a charge needs to reach roughly 30,000 volts per centimeter of gap before it can punch through and discharge. Mars, at less than 1% of Earth's atmospheric pressure, breaks down at around 20,000 volts per centimeter. The gap that an arc needs to cross is shorter. The voltage it needs to cross it is lower. And once the storm is generating thousands of volts against the suit's outer surface, the question is not whether a discharge will occur. It is which component fails when it does. A pressurized suit standing in an open area during a Martian storm is, from a charge physics perspective, the most attractive object in the immediate environment. It is the highest isolated conductor on the surface. The charge gradient will preferentially seek it. This is not a design flaw, it is geometry, a suit that is tall enough for a person, conductive enough to contain electronics, and isolated from the ground by insulating boot material is exactly the configuration that charge accumulation theory predicts will attract discharge events. No redesign of the suit changes this without also redesigning what a suit is required to do. The arc does not need to find a gap in the seam. It strikes the outer shell, and the electromagnetic pulse from that discharge propagates through every conductive pathway inside the suit. Wiring, sensor cables, the traces on printed circuit boards, regardless of what physically separates the shell from the electronics behind it. The suit computer, the telemetry transmitter, the life support control system, all of them sit on the receiving end of a high-energy transient that the shielding specifications were never tested against, because those specifications were written for Earth electromagnetic environments. Earth qualification testing does not include repeated high-voltage arc events from the surrounding atmosphere, because Earth's surrounding atmosphere does not generate them. The engineering community knows this. The Apollo 12 record makes it difficult to claim otherwise. On the morning of November 14, 1969, 36 seconds after launch from Kennedy Space Center, a lightning bolt struck the Saturn V carrying Apollo 12. 12 seconds later, a second strike hit. The discharges propagated through the vehicle's electrical systems, knocking out 3 fuel cells and causing the guidance platform to tumble. Mission Control came within seconds of issuing an abort command. The vehicle survived because Flight Controller John Aaron recognized a specific pattern in the telemetry data and recalled an obscure switch setting that restored power to the guidance system, a recovery that depended on one person's memory of a test anomaly from a year earlier. The rocket did not fail. The electronics nearly did, in a launch environment far more electrically dissipative than any Martian storm, and the margin between mission success and loss was narrower than the mission plan acknowledged. Mars does not offer John Aaron. It does not offer the abort option. A suit computer that fails during EVA on Mars fails in an environment where the backup communication channel, the rescue timeline, and the spare suit are all subject to the same charge environment that just destroyed the primary. The discharge is not the end of the event, it is the beginning of a sequence that the mission was not designed to run. The obvious response to all of this is to ground the suit. Run a physical tether cable from the suit to the habitat structure, maintaining a continuous low-resistance path to ground so accumulated charge bleeds away as fast as the storm generates it. The logic is sound. The tether cable does exactly what it is supposed to do for the portion of the EVA where it is connected. That portion ends when the astronaut moves beyond tether range. The secondary power array the EVA was launched to service is 12 minutes from the airlock. At standard EVA mobility, a tether long enough to reach it becomes a mechanical hazard, a cable dragging through wind-driven dust, snagging on equipment, creating the kind of entanglement risk that EVA planners specifically train to avoid. The tether that solves the electrical problem introduces a mechanical problem that at sufficient cable length becomes equally fatal. A suit that cannot move cannot complete the repair. A mission that cannot complete critical repairs during a storm cannot operate on Mars, because Mars storms last weeks to months. The 2018 global dust storm persisted for roughly 8 months. A mission architecture that cannot conduct EVA during active storm conditions is a mission architecture that cannot reliably function for most of the Martian year. The charge dissipation approach embedded in suit fabric, conductive threads woven into the outer layer, continuously bleeding charge to prevent buildup reaching arc threshold, exists in prototype form. It adds mass, it requires power. At the charge generation rate of an active storm, the fabric system's dissipation rate has not been demonstrated to stay ahead of accumulation. In laboratory testing, it reduces discharge events. In a sustained storm generating charge across an entire suit exterior from billions of particles per second, reduces is a different word from prevents, and the one that matters when the suit computer has no tolerance for even a single high-energy transient is the second one. The Faraday mesh approach, integrating a conductive cage into the suit's outer layer to suppress arc formation against critical internal components, offers partial protection by distributing charge more evenly across the suit's surface and creating preferential discharge paths away from electronics. It also adds mass, stiffens the suit in ways that compromise mobility, and requires that every external connector, sensor port, and mechanical interface penetrate the mesh without creating a gap the charge can exploit. A spacesuit is not a sealed metal box. It is a system with dozens of designed penetrations, each one a potential breach in the protective geometry. Closing those penetrations while preserving the suit's function is not a solved engineering problem. You are 3 months into the surface mission. The storm has been running for 11 days. The habitat's exterior communications antenna shows degraded signal. A storm-related charge event has damaged the antenna driver electronics. Without repair, contact with Earth degrades to emergency-only bandwidth. The repair requires a 30-minute EVA. The storm charge readings at the outer hull are above the threshold where the EVA protocol says wait. The wait protocol does not specify what to do when the storm does not stop, and the antenna cannot wait. Both doors of this corridor lead to the same room. Biological systems need atmosphere. Electronics need shielding. Neither works correctly on a planetary surface where the atmosphere itself is the charging mechanism. This is not a design problem that more sophisticated hardware resolves. It is a constraint imposed by the physical properties of the planet, and the physical properties of Mars are not a variable in the mission plan. The crew of the first crewed Mars surface mission, under whatever program funds and launches it, will land on a world where the atmospheric conditions that make arcing frequent and dangerous are also the atmospheric conditions that made the landing feasible. The same thin air that reduces heat shield requirements and lowers landing mass is the same thin air that provides no moisture, no charge dissipation, no natural protection from the electrical dimension of every dust event the mission will encounter. The engineers who designed the suits will have tested them thoroughly. The question they will not have a clean answer to, the one that will sit behind every EVA weather decision for the duration of the surface stay, is what the charge accumulation rate of a real Martian storm at the actual landing site looks like in real time, and whether the dissipation system embedded in the suit fabric can stay ahead of it, not in the average case, but in the worst case the storm produces on day 43.